All right, everyone. Welcome back. Today we're going to be talking about the heap. What's up with the heap? The heap is an example of a balance tree. So, something I showed you last lecture when we talked about a BST, a binary search tree, is that the efficiency kind of depended on it being balanced. And I didn't show you a way to balance it. BST isn't necessarily balance. That's not assumption that you can make. I showed you how an unbalanced BST could basically amount to a kind of a linear search, right? Instead of being log n. So for example, if we went with an insert and we went with a 1, okay? And then we went and inserted a 2. And by the way, the root of the tree, the root pointer points to that node. And then I inserted a 3 and then a 4. Well, there you go. Now this is basically a linear BST. And if I need to search for a value, well, no more of that log n efficiency, right? We're looking at straight n. So how is a heap different? Well, the balance is you try to basically rebalance the tree to minimize the depth of the tree, because if you have that optimal depth, then you can ensure yourself that you have log n operations, right? And you can have a maximum heap and a minimum heap. I believe we're going to focus solely on a max heap, but that's okay. The same ideas would translate easily to a minimum heap. That also means that every time you go ahead and add something or delete something from the tree, you got to rebalance it. You have to ensure. So, what are the rules for the heap? Well, a node is never less than the entries of its child. Now, this is for a max tree, okay? So basically, the greatest one is going to be at the very top, and then you go down the tree. Also, a tree is always complete. Now, remember the difference between complete and full. If this were a full tree, then every level would be on nodes, whereas a complete tree, every level except the deepest one contains on node, plus a complete tree makes sure that you start to fill that tree from left to right. Okay, so let's look at an example of a heap. Here you go. We've got a 68. The next level has a 35 and a 22. And then after that, we see that the 35 has a child, 10 and 15. So those are less than 35. So we're good to go there. The 22's children are 18 and 19. We're good to go there. And again, 35 and 22 are less than 68. So we have ourselves a heap. Let's look at some more examples. So here, which of these trees is a binary search tree? Okay. So actually, let's do this. Let's copy these over. So first question, which of these are BSTs? And these are the exact type of questions you'll probably see on your final exam. Got a quiz that kind of gets you prepared for that this week too. A little bit more on that later. So binary search tree, remember the rules. The left subtree is always less than or equal to the parent. The right subtree is always greater. So right here, this breaks that rule, right? 15 is not greater than 22. So it's not a BST. How about here? Well, same situation, right? I've got the 1522. So not a binary search tree. What about over here? Same. So all three, none of these are binary search trees. What about a heap? Okay. And again, let's keep in mind the rules. The rules are entering a node is never less than the entries of its children. All right. So it can be equal, right? But can't be less. So how about number 1? Well, 10 and 15 are less than 22, so that checks out. 5 is less than 10, that checks out. 7 is less than 15. So this is yes. Haha. Did I fool you? No, this is not a BST, because there is a second rule that every tree is a complete tree. This is not a complete tree. So if, for example, this 7 was hooked up to that 10, so the 15 didn't have any children, then we could say yes, But right now, no. We want, let's say, to be complete, 7 should be a child of 10. What about number 2? So first of all, let's just look at tree completeness. That looks like a complete tree. Every level's full except the lowermost level, and that gets filled from left to right. So we're good to go there. Let's look at our rules. 10 is less than 22, 5 and 8 are less than 10. 15 is less than 22, and 12 is less than 15. So this is a yes. Now, you might be asking yourself, wait a minute, this looks a little fishy here. I noticed that this 12 is greater than 10, but it doesn't matter what's going on in that tree, right? It's always with relation to the parent. So 10 is not a parent of 12. It is a parent of 15. So it is less than 15, so that definitely works. Okay, so don't get caught up looking at the other subtrees. It doesn't say anything about like it's less than every node at the level above it. It's talking specifically about the node that's the parent. What about number 3? It looks like we have totally complete tree. Not totally complete because that'd be full. We definitely have a complete tree. Let me change that lingo so I don't confuse anyone. What about those rules? 10 is less than 22, check. 5 and 8 are less than 10, check. 11 is less than 22, check. 12 is less than 11, no. These would have to be reversed. So if we swap 12 and 11, then you'd have a heap. So those are kind of just, right off the bat, trying to identify a heap, right? So we saw that of these 3, only one of them's a heap. Let's get back to the lecture now. So let's say we had a heap like this, and now we're talking about how to add things to our heap, and we want to insert a 52. By the way, an insertion like this, at least this part is going to be a log n operation, right? Because the way it works is you insert the 52 at the rightmost location of the deepest level. So what is the rightmost location of the deepest level? It's going to be a right child of 40. So there we go. But now that we've done this insert, this is no longer a heap. We had a heap here. But once we threw in that 52, this no longer became a heap because 52 is greater than 40. Oh, geez. So what do? You fix it by swapping that parent and that child. So now 52 and 40 swap, and we're good. And then you check, is it a heap yet? Well, 52 is greater than 35 and 40, but 52 is not greater than 50. So you continue this process. And this process has a cool name. It's called to heapify. So there we go. We swapped one more time. Now we've got a heap again. And you're not always going to have to go all the way to the top, right? It just happened that for this example, in order to make this a heap, we had to have 52 as the root parent. If we had been inserting like a 45, we would have just done one swap. There'd be a 45 here, 50 there, and we'd be good to go. So this process of rearranging our heap, moving these values, is called reheapification, right? Cool word. And if we are moving these nodes up, I think of it as bubbling up, but just swapping up, that is known as reheapification upward. That's just a fun thing to say, reheapification upward. So that is how you rebalance a tree when you insert. All right. What about when you want to remove a node from the heap? So let's say I want to remove 52. So what you do is you grab the rightmost leaf. So again, there's only going to be leaves at the very deepest level, and you grab the one at the very right and you swap the data with the parent. So I want to remove 52. So 35 and 52 are going to swap places. And once that's done, I remove the 52, what I was trying to delete. So all the right nodes are there, but they are no longer in a heap. They're not in the correct order. So I have to rearrange the tree. I have to rebalance this tree to make sure that the rules are met. Right now, 35 is greater than 20, but 35 is not greater than 50. Does that make sense? So because we break those rules here and here. So what do we want to do? We want to swap 35 with the largest child in order to maintain the heap rules. And at this point, first swap, we're back to being a heap. But if this was a larger tree and you'd have to do more swaps, and that's okay. You just continue to swap with the largest child until a heap is a heap again. So this is another example of reheapification. However, we're no longer moving up, we're moving down. Therefore, it is called downward reheapification. What a cool word, right? Reheapification. I wonder if that works in Scrabble. Or I haven't been playing Scrabble. I'm playing Words with Friends, which basically feels like a Scrabble ripoff. They just have different sized boards sometimes. In any case, if you want to implement a priority queue, a heap is great. The highest priority goes to whoever's up top, and that gets processed first. So really neat data structure. Now, you can implement this a couple of different ways. When we learned about a binary tree, we saw an array implementation, right? We saw a way to do it. We did it with nodes ultimately, and that's where we spent most of our time doing this. We've done it with nodes, but you could do it using an array, right? We talked about how if you wanted the parent index and you had the child index, you could use this formula to find the parent. Or if you had the parent index and wanted the child, right, you could figure out what the left and the right child would be using these formulas. And the important thing to remember is we have integer division here. So whenever we divide, you're always going to get a whole number, which is great because those indexes should be whole numbers, right? We don't have half indexes. So I'm not going to make you implement this from scratch or using nodes. What I can do instead is I've uploaded this to Canvas and you have an implementation. Oh, and I've already ran it, right? This time I was smart. I'm like, I'm going to run it before the lecture, make sure there's no weird bugs. But this is done. I used a vector instead of an array, but here are some functions that'll look familiar. There's got to be some bubbling up, some bubbling down, some swapping. Here's how to get the left and right indices, the parent. Boom. So those are the private functions. We don't want anyone to call these. Instead, you would call the constructor, insert, remove, top, and get size, right? These are the functions that would be most relevant for our binary heap. So I encourage you to go through, check out the code. It's not complex code, so definitely spend a little bit of time checking it out. The bubble up and the bubble down, I think, are the most interesting. You might throw in the top is not right, but maybe remove. But let's run the code. Right now, what it's doing is it is creating a heap. It's seeding the random number generator. It's adding 10 random values from 1 to 100. And then it prints out the top of the heap. And as there's items on the heap, it removes them. And the cool thing to keep in mind is every time you remove, this tree gets rebalanced. So what we should see as we're going through this while loop, even though these values are not being inserted from greatest to least, right? Because this is all happening randomly. There's going to be big, small numbers. As we move items off of the heap, we should see them being removed from greatest to least because every removal will rebalance and then the largest number goes up top, okay? So let's run it. Well, let's compile it, I guess. Let me compile it to show you that portion. There we go. Let's run it and check that out, right? So we see our values. Our heap had a 93, 85, 74, so on. You guys can read numbers. And let's run it again. We see a different set of numbers just to prove that it's not like hard-coded. Different numbers every time. So that is pretty cool. You will have to work with a heap for the lab, but one kind of cool aspect is, and here's the sample code we just saw, is there is a built-in make heap function in the algorithm library of C++. So what you can do is it turns any data structure with an iterator into a heap using an ON algorithm. So ON in order to make a heap. And let's remember, every time you insert or delete is a log n operation. Why is it a log n operation? Well, keep in mind, you basically, all of them involve going down to the lowest level to the rightmost leaf or node. So that's a log n operation. But you also have to pay the price to balance the tree. So that should also be a I'm sorry. So I'm confusing myself. So it costs log n to do add or delete, but as you're building this, the cost to make the heap is on. Therefore, the cost to make a heap using this process is on log n. So make heap is on, inserting is log n, so you have to kind of multiply those together to get you your final time. So if you had an array named data size n and you wanted to call make heap, then this would be the beginning and this would be the ending iterator. But what if you had a vector? Like, guess what you'll have to do for the lab? Let me show you. I won't leave you hanging. Let's do a small vector here. So vector, oh, I know, that's TD vector, huh? Let's not forget that. So a vector of int, we'll call it v, and I'll use an initializer list, 20, 30, 40, 50, 25, 15. And then you call make heap, and it needs the beginning and end. And that might have been a make end. I said end and I wrote end. A make heap. You might have guessed it. I said begin, end. And those are functions of the vector class. So you'll be able to invoke v.begin. And this is a function, so don't forget your parentheses. And why is a comma way up there? Bizarre. And invoke end. And that will make your vector into a heap. And then what you'll just have to keep in mind as you're working is that if you ever need to refer to the parent or child indices, you've got these. You'll also want to look at the sample code as well to kind of get you through it. Okay. So that is the end of our heap lecture. Not too long a lecture, cool new data structure. We've got some experience now. So hopefully this just changes the rules a little bit for you. If you have questions, as always, email, Zoom meetings, all of those are great avenues. Okay, thanks.